Hello, everyone. Welcome to our first webinar on plastic circular economy. My name is Mer Niku. I'm Senior Manager of Sustainable Materials with Alberta Innovates. Today, I'm the host and moderator of the webinar. I'm going to start with a 10-minute introduction into our program and what type of initiatives we are supporting. And then I will pass it to our speakers to talk about their presentations and projects. And at the end, we have some time for Q&A. Before we start, we want to respectfully acknowledge that Alberta Innovates is situated on traditional territory of the Treaty 6, 7, and 8 First Nations, home to Métis settlements, the Métis Nation of Alberta, and regions 2, 3, and 4 within the historical Northwest Métis homeland. Alberta Innovates, along with its two subsidiaries, InnoTech Alberta and Seafair Technologies, has 11 different locations in the province with the total employees of 589 and an operating budget of $250 million. The total number of active projects are over 1,300 with a total portfolio value of $1.2 billion. Within Alberta Innovates, there are different groups. One of them are divisions. One of them is called Clean Resources. That is a merger between clean energy and biosector. Clean Resources has 5 different groups. One of them is called Sustainable Materials and is the group that I'm part of, and we are going to talk about that group and the scope of our work. A few months ago, actually May this year, 2 programs came together, bioindustrial materials and bioenergy and circular economy, to form this group. The scope for the projects and initiatives that we support at the moment is everything that is in this slide. Using different type of biomass, especially if it's underutilized, such as agriculture and forestry, residue and waste, or different type of waste stream, either is organic portion of municipal solid waste or plastics or any other type of waste, basically, to make different type of products or sources of energy, renewable fuels, chemicals and polymers, and construction materials. This is a big picture of what we are supporting, but to stay on circular plastic, that is the topic of our conversation today, I can say that this area is a new addition to the program that has grown in the last 2 years. The whole reason for circular plastics and adding this focus area to our program was the conversation that started within government of Alberta, with the goal to establish Alberta as a North American center of excellence for plastics diversion and recycling. The reason is to send less plastics waste into landfills, transform some of that waste into resources. Also, Alberta, as the second largest producer of petrochemicals in Alberta, has a great opportunity to make a real contribution in this area. The last 2 years and adding this focus area to our program has been a close collaboration with 2 key ministries, Alberta Energy and Minerals and Alberta Environment and Protected Areas. One of the initiatives that we started together, 3 of us, plus contribution from Prairie Scan, is this study that we recently completed, and it's called Plastics Feedstocks Assessment. This study is looking at how much plastics waste we have available in Alberta, not just generated, but also potentially imported from other provinces or even some of the states. The other study we completed is the one that InnoTech Alberta has done, and is called Innovation Gap Analysis. This is our first presentation, actually looking at the results of this study. So we are going to learn more details about this study shortly. The other study that was completed, led by Alberta Agriculture and Irrigation, is called Bioplastics and Sustainable Packaging in Alberta. We have completed the first phase. That was a small study, but now we are trying to basically brainstorming with our colleagues in the ministry to scope the next phase for this study and hopefully looking deeper into some of the more technological aspects and supply chain and all of those kind of details. The other activity that we do, and probably that's what we are famous for, is funding innovative projects. what is really important for Alberta Innovates, showing in our name, is about innovation. And it's really focused on technology development, not business innovation, not innovation in the way we educate public. They are all important, but where we play a role is really on the technology side. The type of projects that we support are at the technology readiness level in the range of 3 to 7. Our application process is a continuous intake, meaning is open throughout the year. At any point, we can bring in an application for evaluation. We are thinking about a competitive call, but the scope and timeline has not been confirmed yet. Our focus is really on applied research, the projects that have commercialization potential, especially they need to show that they are going to realize some impacts in Alberta. The project team can come from anywhere, does not need to be Alberta-based, as long as there are clear connections to the province and environmental, economic, and social impacts can be realized in the province. When we talk about technology, is not just one piece of the supply chain, is the whole supply chain, because we understand the importance of basically development in all different pieces of the value chain. Some of the projects we support right now are more focused on using more sustainable feedstocks, like bio-based plastics. We are also looking for innovation related to recycling technologies and what we call enabling technologies. If you have the best infrastructure for recycling, if you do not have the right sorting and collection of waste, then what's the point? Or you have all this recycled content, but then you don't have any industries to use this recycled content in the new products, what's the point? So for us, it's really about different pieces, like enabling technologies, examples like waste management practices, tracing plastics in the life cycle, and using some recycled content in the new products, all of those kind of aspects. The other factor that is very important in this space is design for circularity. We should not be thinking about end of life after we use different products. Thinking about end of life has to start from design. When the resin is designed, or the products are designed, or even what type of glues and labels are going on different products. This is a very important piece, and we really want to see also some innovation related to that. One example of the projects that we support, we approved funding for the project that Nate right now is leading, is our second presentation. And again, we are going to learn more details shortly. The last piece is our collaboration between Alberta Innovates and Emission Reduction Alberta. On the technology scale, this is how we are working. Our focus is more on the lower TRL, and then for ERA, it's higher TRL and through commercial application. And we always talk about ERA as our closest partner, but I feel like so many people don't know how closely we work together. We are basically involved in the whole project lifecycle, starting from the evaluation of different applications, contracting, project execution, and project closeout. ERA normally operates based on competitive calls, but there are some opportunities for project hands-off between AI and ERA, or even some co-funding. Another example is the project that we are going to hear from. Our third presentation, Circular Rubber, is the project that came through the Circular Economy Challenge that ERA had last year. I was part of the whole evaluation process, and right now I'm advising this project. And just to give you a sense, speaking for myself, on average, 30 to 40% of the projects I'm advising come from ERA. So by that, this is the end of introduction. You're welcome to send in your questions at any point, but as I mentioned at the beginning, we are going to respond to your questions at the end of the presentations. So now I'm going to pass it to our first speaker, Karen, please.
All right, I'll just start the presentation here. Good afternoon. It's a pleasure to be here. My name is Karen Budwill. I'm a senior researcher at InnoTech Alberta, and I'm going to be talking about the innovation and technology gap review that we did for Alberta Innovates on plastic waste management. So just a brief introduction to InnoTech Alberta in case people on the call here are not aware. As Mayor mentioned, we are a subsidiary of Alberta Innovates. We are a research and technology organization that helps to works with companies and industry to help de-risk technology development from proof of concept to pilot scale testing. We are organized into 5 divisions, as you can see here: energy, advanced materials, environment, bioindustrial, and applied chemistry. I'm part of the environmental team. We have several facilities across Alberta. The main building is here in Edmonton, as you can see in this picture. So, as Mayor mentioned, they approached us to help with performing a technology gap analysis for them across the entire plastic waste management chain. So that helped them understand some of the challenges, the innovation, and some of the research gaps that exist with plastic waste management. And the final outcomes were then to identify key innovative opportunities in plastics recycling, as well as the whole circular economy of plastics, from plastic manufacturing to upcycling. And I just want to take an opportunity here just to acknowledge the team members who helped me with this gap review. That's Tridong Ngo and Atala Khan Mohammed. So the main drivers, Mayor had touched a bit on this, about what's driving this for this gap analysis. So this statistic here, I think, was from 2016, but I think it's still pretty applicable for today. That only, of all the plastic that's, there's 3 million tons of plastic that's discarded in Canada every year, and only 9 to 10% of that is recycled or diverted. So there's a huge waste of plastic. And that has driven a lot of strategies to reduce that. So like for the federal government, the zero plastic waste strategy, to have a target of zero plastic waste by 2030. Mayor had mentioned the government of Alberta natural gas vision and strategy that Alberta will be established as the Western North American Center of Excellence for Plastics Diversion and Recycling by 2030. And then more recently, the government of Alberta put in an extended producer responsibility regulation. So EPR is a program that transfers, a regulation that transfers responsibility and the costs of waste management of plastic or single-use products, packaging, paper products, and hazardous and special product systems from municipalities to producers and manufacturers. And this includes plastics, both rigid and flexible. And the idea here is that this will help foster changes at the producer level, the manufacturer level, to reduce the amount of plastic that's used in their packaging, or to use alternate polymers such as biodegradable plastic. EPR systems have been regulated and are introduced into several jurisdictions across Canada and the US. And so this just came in here to Alberta, and I think by 2025 there's supposed to be systems in place for EPR to occur. Just a quick note about terminologies for plastics recycling, because there's a lot of terminologies that mean sort of the same thing, but are used by different people. For this gap review, and just to keep things simple, we went with ISO definitions. So for mechanical recycling, it's the processing of plastic waste into secondary raw material or products without significantly changing the chemical structure of the material. Whereas chemical recycling is the conversion to monomer or production of new raw materials by changing the chemical structure of the plastic waste through different means such as gasification, cracking, or depolymerization. So our approach to this gap review or technology gap review was to look at the whole life cycle of plastic. We started off with mechanical recycling because that is the dominant recycling process used. It's pretty well established and will continue to be so. So we looked at innovation technology gaps with mechanical recycling. We then looked at chemical recycling, followed by kind of narrowing in on some of these difficult to recycle plastics and polymers that will just end up in the landfill. We then looked at innovation technology gaps with polymer material design for enhanced recyclability. Then we looked at upcycling, so value-added products from chemical or from recycling. What was out of scope for this project was pyrolysis or fuel to energy. So that was, we did not focus on that. So to start off with mechanical recycling, the main challenge with mechanical recycling is that there's a need for pure plastic waste streams because the quality of the plastic recyclates is strongly dependent on the quality and purity of the input stream. So when you get mixed plastics coming in from garbage collection, going into material recovery facilities, there's sorting that has to be done to separate these plastic streams. And it can be quite time consuming, especially if it's all done by manual sorting, and there's a high potential for loss of material. So some innovative solutions that have occurred is with advanced sorting, and this includes such things as tracers, for example, ResiChain that's being developed by BASF. And this is a chemical tracer or barcode that's put into the plastic. And so you can trace the whole life cycle of the plastic through its use and discard and then recycling. And I should say Alberta Innovates is supporting a pre-commercialization trial of ResiChain in Alberta. Artificial intelligence is being used now to assist plastic sorting. And it's actually the Alberta Edmonton Waste Management Center is actually trialing out AI robotics to help with this sorting of the plastic. On the flip side, there's some new or lower TRL processes that are looking at recycling mixed plastics together so that you can just eliminating having to sort them. And for example, you can chemically fuse some of these plastics together and produce pellets from them. So for gaps, there's still a continued need for enhancements to increase sorting accuracy and material retention, and then a validation of processes that claim to be able to recycle mixed plastic streams together. So sorted plastics may still not be suitable for direct reprocessing or recycling due to contaminants from colorants, additives, adhesives, fillers, and things like that, or as well as from consumer use, because they can result in yield losses during the recycling process. What's usually done is there's a washing step, but that can be costly because you need a dedicated washing equipment and drying system, and then you have to deal with the wastewater. So some of the innovative solutions is using solvents to solubilize and then remove some of the contaminants. So this is not, even though it's a solvent, this is not considered a chemical recycling, it's still mechanical because it's not actually breaking down the polymer. But it's still, there's a downside to this because there's how to deal with these toxic solvents at the end and needing to separate the polymer from the solvents. So there is some novel work being done using supercritical CO2 as an alternative to this. And there's a technology research organization in Spain that's looking at this, and they have been able to effectively remove some volatile organic compounds from low-density polyethylene film using supercritical CO2. So again, some of the gaps then is still there's a need for innovative pre-treatment or post-treatment technologies that increase material retention and quality, and then to understand and address some of the environmental impacts of process, especially when there's some solvents being used, and some of the energy efficiencies around that. Turning to chemical recycling, there's a lot of different types of chemical recycling that are being tested or developed, and I just for the sake of time, I'm just going to focus on two of them. The first one here is solvolysis. So this is using solvents now to depolymerize, to break down the polymer. The main challenges with this is it requires a lot of energy and water and operating temperatures. And then there's also the challenge of separating the solvent and other byproducts from the monomers. So some innovative solutions is using supercritical fluids like supercritical water, as in this diagram here. So you can fine tune the temperature, the pressure, concentration, and with supercritical water, and make it catalytically active to break down the polymers. There's some research looking at using alternate solvents such as bio-based solvents to get around some of that toxicity issues. And then there's some alternate treatments to solvolysis using mechanochemical treatments. So this is using mechanical stress to break open bonds, for example, using ultrasonic bubbles to break up polymers into oligomers to improve solubility. So there's still a lot of gaps in optimizing these processes. So getting optimizing solvents, decreasing water use, or looking at ways that minimize the use of solvents, and then addressing some of these environmental impacts. Another chemical recycling process is using catalysts. So the challenges with using catalysis is that it's very complex. This process, there's a lot of rate-limiting reaction barriers and reaction thermodynamics using catalysts to break open the polymers. And you really need to know the chemical compositions and the physical boundaries of the plastic. So the molecular weights, the melting points, the crystallinity of the plastic. So some innovative solutions then is there's a lot of work looking at improving or optimizing catalysts that can enable rapid kinetics on solid surfaces, so you don't have to do a lot of pre-treatment of your plastics. And there's quite a lot of work too looking at biocatalysts. So this is enzymes from microorganisms that can degrade the polymers. So there's a lot of work on bioprospecting for novel enzymes, and then including genetic engineering for these novel enzymes. And there's some work being done to combining this, a hybrid chemical biological catalysis system to enhance degradation, particularly these crystalline regions. So these are still fairly low TRL. So there's still a lot of work to be done on optimizing these catalysts, whether they're bio or non-bio catalysts, so the range of plastics that they can be used on, whether you can have mixed plastics or different enzymes together, reaction rates, product inhibition relief, and then the optimization and recovery of these depolymerized products. Turning now to the difficult to recycle plastics. So the reason why some of these waste plastics are difficult is presence, like for PVC, polyvinyl chloride, is the presence of additives such as stabilizers, colorants, or plasticizers. So, and then there's a type of plastic called thermosets, which such as polyurethanes, epoxy silicones, that are traditionally difficult to recycle, because once they are produced or shaped, they can only be shaped once or made once because their polymerization creates this 3D network that can't be remelted or solubilized. So to get around that, some novel solutions are using some solvents. So I've kind of talked about this in some of the previous slides, to remove the additives and dissolve and purify. So this is being done like with PVC and polystyrene, for example. In terms of for the thermosets, there's some interesting work being done where they called vitrinization, where it's chemically alters the structure of the thermoset to enhance the recyclability without compromising mechanical properties. So it's introducing some sort of different types of degradable cross-links in the polymer structure that helps them to break down at the end of life. So for gaps, then there's still lots of work to be done to optimize the solubilisis process for hard to recycle thermoplastics and thermosets. The integration of this with current recycling facilities, there's some work to be done there too, and then redesign and manufacturing of thermosets with inherent recyclability is still at a low TRL, needs lots of work. Turning now to material design for enhanced recyclability. So this is sort of going back to making novel or new plastic material that already has a built-in recyclability and lower environmental impact. This was brought up in a recent document published by Canada Plastic Pact, which they called their golden design rules of using less and better plastic. And in it, they mentioned that new plastics should be additive free, and monomaterial plastics should be used as much as possible, like for example, for flexible packaging. So indeed, there are companies that are actually looking at this and producing materials that are additive free and single type of plastic, like for snack bags and things like that. Another interesting innovation that's occurring in the EU with a research group is that they're making plastics with this tunable degradation capability. So, for example, when they're incorporating some enzymes into their adhesive that will glue together two different types of plastics. And so at a predetermined time, like at the end of life of the plastic, the enzymes will become active and degrade that adhesive layer and will separate the two different types of plastics for ease of recycling. So there's a need for continued optimization of these types of design for recycling plastics, and a verification that their physical mechanical properties are not compromised during redesign. So upcycling of plastics, this is the breakdown of plastics into specific oligomers or monomers with upcycling into value-added products or materials. The challenges are the market demands for this and the operational costs, and then the product yields and purity. So innovative solutions, there's so many different solutions and research being done on this. And so I've just highlighted just a few here. There's selective conversion of high density polyethylene through chemical recycling into value-added acids, like acetic acid. And this interesting one here that was recently published last year looked at a tandem chemical oxidation bioconversion of mixed plastics into target products. So they first did a chemical oxidation step, and with these intermediates that were produced, they fed into a bioreactor that had a genetically modified bacterium that then converted those into these bioproducts that for the bottom one, the polyhydroxyalkanoids, is a biopolymer that could be used as a biodegradable plastic. So there's still gaps in process optimizations to ensure that upcycling technologies are cost effective with minimal environmental impacts and efficient recovery of value added products from the system. So in summary, if the goal is here to have establish Alberta-based plastic circular economy, it's a very complex system. There's no one size fits all technology or solution that will manage all the plastic waste. So there's lots of pieces to this puzzle, including in continuing innovations in recycling plastic material design upcycling. And if I can put a quick just say that this is where Alberta Innovates, or InnoTech Alberta likes to play, is help with this innovation in recycling. Mayor mentioned this, but I didn't go into this either, is that an important piece of this puzzle is knowing the plastic waste volumes and types in Alberta. And so that research, I guess, is now completed. So it will be interesting to look at that. And that will definitely fine-tune what kind of technology can be applied best to the waste that's generated in Alberta. Another piece of the puzzle is knowing the market pool for recycled and upcycled polymers. There's also the development of alternate bioplastics and biopolymers production. And then there's the regulatory drivers, such as EPR and track and trace. And that is the end of my talk here. And I just want to acknowledge funding from Alberta Innovates for this talk, for this gap review. And I look forward to any questions you have at the Q&A session. So I am going to now pass it on to the next speaker, Paolo.
Good afternoon, everyone. Let's see if I can share this in presentation view. Oops, there we go. Good afternoon, everyone. I am Dr. Paolo Mussone. I hold the Ovintiv Applied Research Chair in Energy at the Northern Alberta Institute of Technology. And I'm really grateful to Alberta Innovates for the invitation to be here today to talk about what NATE Applied Research, my team, are doing in the area of plastic circularity. I titled my presentation today with the headliner "Designing for Circularity," because that really is at the heart of what we're doing at NATE in this space. And as we go through the presentation, I will highlight how what we are thinking in terms of plastic circularity and applied research, specifically with that, is really about developing a platform. And a platform that right now includes a certain number of actors and funders, but it's built with flexibility in mind so that we'll be able to grow, sustain, and make it more effective going forward. For those of you that may not be as familiar as some other ones about NATE, the Northern Alberta Institute of Technology, the Institute has been around since 1962. Applied research is a little younger than that. It's been around for about 15 years or so. Has experienced a lot of growth over the last 5 years or a little longer than that. And it's currently organized as a portfolio across 7 applied research centers and teams. I lead the Clean Technologies team and currently staffed with 20 individuals, all excited, getting out of bed in the morning and looking forward to working on solving environmental sustainability and industry problems. So the team really exists with that vision to create knowledge that marries environmental sustainability with economic prosperity. And our approach to marrying these two is by adopting what we call principles of the circular economy. Both Mayor and Karen mentioned and talked a little bit about these two. As they apply to the work that we're doing, we're really referring to 2 principles. One is that there's no such thing as waste, especially in the plastic space. And the other one is designing so that the waste that may be generated at the end of the manufacturing process is as minimal as possible. My team works across a number of circular economy topics. The plastic circularity in particular is the largest component of my program right now. And the work that we're carrying out in this space and that we participate in executing in this space has its origin in NATE's partnership with the Heartland Polymer. This is a 10 million, 10 years research collaboration activity that Nate entered into with Heartland in 2019, and the largest in Nate's history. And it's a partnership that involves a company which is Interpipeline's polypropylene brand, Heartland Polymer, currently operating a world-scale infrastructure production facility just outside of Edmonton and Fort Saskatchewan. This is an integrated propane dehydrogenation and polypropylene complex, the largest in Canada, as mentioned, one of the leading ones in the continent. The partnership between Nate and Heartland Polymers, at the heart of it, was created to develop solutions to ensure that plastic waste is minimized and that whatever plastic waste is out there is reused and considered a valuable resource, and so turned into a feedstock for development of new, useful, sustainable products. And the vision for this, of course, is to reduce environmental impact for the plastic industry overall. Very importantly and central to all of what we do at Nate, and definitely at the heart of all the projects that I'll talk about with you today, is Plastics Research in Action's commitment to practical, hands-on opportunities for all students and for graduates as well. And this is important because technology development is definitely essential to driving plastic circularity, but having trained hearts and hands and minds that are going to be able to really drive those technologies into implementation is just as important. And so we're very happy to use some of the funding that we have set aside for students specifically. There are currently 4 projects in the Plastics Research in Action portfolio. 3 of them involve my direct participation with my team. The titles, I reported them here. The first one is a project that involves a number of partners and is really focusing on using recycled plastics materials in asphalt applications. The second one is a project with a small and medium enterprise. We'll talk about it more in a moment in details. That is about designing flooring solutions using recycled materials. The third project is about using post-consumer recycled content for building applications. And the fourth project, for which I'm especially thankful to Alberta Innovates for the funding, is a project that has a very long view on developing applications for polypropylene blends that include the utilization of post-consumer recycled plastics. The first project, the one that is looking at developing new asphalt applications, is a large partnership that Nate entered into, a project led by the Senior Project Manager for Plastics Research in Action. It's a partnership that involved a company called Green Mantra Technologies. The company focuses on taking post-consumer recycled polypropylene, amongst other plastics, and turn them into waxes. These waxes are amenable to be introduced in asphalt binders, and then in this way displace some of the existing binders that are used. It's also a project that hinges on partnership with the binders themselves, the binder producers themselves, and this is why McAsphalt Industry, as well as companies that lay asphalt like Alexander First Nations Asphalt and Concrete Burn Co. are involved into this project. The project is also a very significant partnership because we have taken the research that was carried out at the bench into the field. And in this case, field means laying stretches of road and parking lots using this new product that was developed through this research. And this is done in collaboration with Heartland Polymers at their site, but also with Strathcona County and the Sturgeon County. This is work that's now entered a really mature phase in terms of the execution. We're monitoring the health of those and the properties of that new asphalt that has been laid. And at the end of in the month of November, there will be an update through Plastics Research in Action on the outcomes of that ongoing project. The second project that I mentioned, this one in execution in my portfolio, is a partnership with Calgary-based Polyco. The company is developing a process to incorporate post-consumer recycled content of different types into polypropylene for the purpose of creating a fluorine product that is intended to displace polyvinyl chloride, typical fluorine solutions. These types of fluorine solutions are very significant, especially in the commercial real estate space. And the company has achieved now a state where, in fact, we've demonstrated that it's possible to include this post-consumer recycled plastics into the virgin polypropylene feedstock without significantly lessening or deteriorating the properties of the tiles themselves, the fluorine products themselves. This is also research that's ongoing and will be reporting at the same event in November. Third project that's currently underway is with a company Edmonton-based called Rewaste, and also with another company Edmonton-based is called Clark Builders. Through this project, we are developing, based on plastics recycled from Rewaste. So in this particular case, it's our industry partner that's sourcing the plastic, the post-consumer content, and processing it. And we're developing applications that are targeting the construction industry. The goal of this project is to develop concrete formworks. So the end goal of this is like the creation of these sheets of plastic that would displace plywood and other wood-based materials that are commonly discarded at the end of their life, at the end of the project, of the construction project. In this case, the plastic product is going to be designed to have a much longer lifetime, so recycled over multiple iteration of construction sites, and at the end of its life, be recycled further into other applications. I mentioned that Alberta Innovates is supporting one of these projects, and it's the newest one, the most recent one in the portfolio. This is a project in collaboration with Heartland Polymers directly. This is, as I mentioned, a division of Inter Pipelines. And the project will focuses on the development at the laboratory and also pilot scale of prototypes that will include various sources of post-consumer content into virgin polypropylene. At this point of time in the execution of the project, we're working with 4 different sources of post-consumer recycled content. We've been sourcing these from commercial suppliers, both in Alberta and also beyond the provincial borders. Oops, wrong direction. At the heart of all these projects are, and especially at the heart of the last project, are 2 important applied research questions. How do chemical, physicals, and thermal properties of PCR content affect the performance of these new products? Karen showed us that a lot of work is happening in the area of removing contaminants as opposed to additives that have been added to plastic products. And we know it's known in the literature, and companies have already experienced this, that having these types of modifiers, additives, plasticizer, colorants, inorganic materials, what have you, that is added to plastic, makes it really difficult for PCR to then be recycled without any form of treatment. We don't know, however, yet in detail how all these types of properties affect the final properties of a blend. And at the heart of all these projects that I've showed you is really an attempt to understand these types of correlations. And finally, very crucial to all of these projects, which are built on an initial phase where we're doing laboratory work, scale work, and then a subsequent phase where there's pilot scale type activities, is understanding how the data that emerges from doing laboratory scale activity, particularly on the physical, chemical, and thermal property side, may scale when we embark on pilot scale facilities. Understanding those correlations, understanding that linkage is critical, because moving forward from bench scale to pilot scale facilities, the cost involved become very large. And so having a real good understanding of that transition is important so that companies use funding in an efficient way when attempting to scale. The applied research model that we've taken for all these projects, and particularly for the one funded by AI, is a sequential one, and it involves an aspect of iteration in the back end. There's an initial phase where we characterize the post-consumer recycled content. This is important for the reasons that I outlined before. All of the additives and potential contaminants that are included in these materials will inevitably impact the properties of the product at the back end. So understanding what that looks like in the front end is important. It's also a stage that acts as a screening as a screening stage. There may be some PCR that simply are not suitable for PCR content that may be simply not suitable for applications. The second stage of the project is one in which the PCR content is incorporated inside a virgin plastic matrix. And this is done in the project that I talked about through mechanical means. And the way we do it at the bench scale is by using a microcompounder in which we create cubic centimeter scale quantities of these new plastic mixes, and then using a microinjection machine to create samples that then we use for testing. And testing is the last stage of this applied research model, this applied research progression. We evaluate those prototype materials by measuring the mechanical properties, the thermal properties, and how they behave, for example, in an environmental, in different environmental settings. At the same time, those prototypes may be used to scale and then carry out the same type of experimentation, but on a much larger scale. And crucial to all of this work that involves experimentation and lab and pilot scale testing facility, there's an element of techno-economic assessment. We pair all this data with capability that we have at NATE to make sure that a technical solution, a scientifically sound solution, is also one that can scale and make sense from a techno and economic perspective. Diving a little more into the details, the properties that we characterize for the PCR content are their thermal properties. This is important so that we can understand when the materials, for example, start to flow, or when the materials may start to degrade when they're being heated, as an example, where the transition, thermodynamic transition points are. We study their chemical composition, and this is probably the most important aspect of carrying out this type of characterization, because alongside with the dominant plastic that they're made of, there's also a broad range of many other chemicals that come along with them. We also characterize their physical and microscopic properties. Oftentimes, these materials are well, the vast majority of them, in fact, are composite, and understanding how the elements that go along with the main plastic component, how they're blended together, is also important for us to be able to determine what's the best way of creating the blends in the second stage of the experimentation. I alluded to the determination, identification, and also quantification of organic and inorganic impurities. This is an emerging area of interest, not only from a processability point of view, but also from a long-term environmental sustainability point of view. Central question that is becoming more and more asked is whether these new materials that will contain PCR content are environmentally safe. Understanding which content you start with in terms of organic and inorganic impurities will be increasingly important. And so we're working towards carrying out that. In terms of our projects, and specifically for the Design for Circularity project funded by AI, compounding and extrusion are the heart of the creation of these new materials prototypes. And this is done at NATE at the bench scale. And in terms of piloting, this is work that is carried out in collaboration with external providers, and so with collaborators that work with us on these projects. In terms of measuring the mechanical, thermal, chemical properties of the prototypes, we have the ability to carry out the majority of this type of testing in-house. But applied research being a team sport, we also partner when it makes sense and when the project needs with external providers. In some of the projects that I showed you, that I talked about earlier, we've partnered with also other institutions across Alberta to execute the scope of work when that made sense. Project funded by Alberta Innovates was kicked off at the beginning of April of this year. And that was a really important initial phase of the project that continued, in fact, throughout the summer. It involved efforts in acquiring and then starting to characterize the post-consumer recycled plastic contents that are going into these plastic prototypes. This work is now completed. Pictures of the samples that I showed you earlier are the samples that we're working with. And so that part of the work is wrapped up. However, this is a project with a long time horizon ahead of us, as you can see. So we'll continue to keep our ear in the ground and our business development team active in making sure that new suppliers and companies that come to the fore with commercially scalable, commercially available PCR content are made aware of this project and hopefully can participate in a subsequent iteration of this. The phase that we're in right now is the one in which we are creating blends of polypropylene and some of this post-consumer recycled content that I showed you about at the bench scale. This will involve commissioning new equipment for us at NATE, and then getting started with creating the content that will be tested. And in the new year, and also and in the year and beyond, carrying out the characterization of those blends, and alongside with that, building the techno-economic assessment for all of those new blends. The outcome of this work is going to be a selected number of formulations, optimal formulations, as we refer to them, that will be then scaled in a pilot facility. So at the end of that exercise, at the end of the pilot scale facility, we'll have characterized the product that Heartland Polymers will be then ideally ready to take on and start producing at a larger commercial scale. And of course, at the end of the project, we'll be required to report to both vendors. The project funded by Alberta Innovates is also an example of building a new value chain. I call it a fledgling value chain through applied research. This is because the project links, on the one end, post-consumer recycled content providers, manufacturers, processors, companies that already are active on the market and that have these products available for purchase. But at the same time, it links plastic compounders. These are companies that typically buy virgin plastics and create new products with them. The project would link the two of them because through this applied research, we'll be able to determine new plastic formulations that could be potentially scaled. And on the back end, importantly, the applied research being driven by a company need, Heartland in this case, will also have a direct tie to the market. The choice of the formulations that we are studying right now at the bench scale, and the one that will ultimately be scaled when we go to pilot scale, is driven by market needs and by market opportunities. And alongside with those comes, of course, the entire value chain that's represented by retailers and ultimately markets and consumers. So applied research in this sense as an enabler of a new economic opportunity for an entire value chain. Of course, this work doesn't happen in a vacuum. It's a result of a large team that every day works to make these things happen. The picture here represents myself with individuals that are immediately involved in the Alberta Innovates funded project. Dr. Mohamed Arshad, shown on the left-hand side. Emily Devereaux is our technologist, pictured in the center, and Kelsey Doage, also research lead on the project, right beside me. Overall, the plastic circularity portfolio at NATE, funded through PLEA, has counted over 10,000 hours of highly qualified personnel training in laboratory technique, but beyond, also field pilot scale level techniques over the last few years. And I'm very proud to highlight how we've been able to achieve 0 safety incidents in carrying out all of that work. The team is hiring. So if there's any students out there looking for a wonderful opportunity to work on an exciting project for the next calendar year, we're looking for a position to fill a position, someone that will work as part of our team working on the Alberta Innovates funded project starting in January of 2023. So a great opportunity to work both in the lab, but also with an eye to getting some experience also in pilot scale activities. And I will close by gratefully acknowledging the funding that makes this last project possible from Alberta Innovates, and the generous funding from a Heartland through Plastics Research in Action for the entire portfolio, and also for this project in particular. I thank all of you, and if you have any questions that are technical, scientific in nature, please feel free to reach out to me. We have a fabulous business development lead individual, Mike Che, who is able to take all the questions and comments you may have on the business development side. And finally, I will be remiss not to mention Dr. Toyo Yedun, who is our Senior Project Manager for Plastics Research in Action. Please reach out to Toyo if you have any questions specifically to Priya. And with that, I wish to thank everyone for listening. And if you have any questions, I'll be around to answer. And with this, I will pass the virtual mic over to Bram.
Thank you, Paolo. While I get started up here, my name is Bram van den Berg. I'm the COO of Circular Rubber, and we are a waste-to-value company specialized, or we strive for the infinite use of the world's rubber, focused on the mining sector initially, and then we plan to roll it out later. We're a circular economy play, waste to value, and we're transferring a linear problem into a circular problem. As a little bit of background, over in the last World Economic Forum, circular material use, it's actually circular material use is going down year over year, which is obviously going in the wrong direction. Especially with legislation coming into place, European Union placing 50% circular material use by 2030, 100% circular material use by 2050. We need to change this behavior. And we're addressing the linear problem of mining industry tires, which for decades have been stored on the mine site, either as retaining walls or basically landfilled on site, and an additional 1 million ton of mining tires is added to this pile every year. End-of-life tires are typically buried. Like I said, they create operational challenges because they're a nuisance from a sheer size perspective. There's environmental concerns and safety hazards. And many of the mining operations have a significant liability on their books for end-of-life mine closure obligations to deal with this problem. In addition to those problems, we obviously see environmental impacts. In case a pile of tires does catch fire, it's typically uncontrollable. We've seen them in the past. It's obviously something to be avoided. Landfilling on site can create heavy metals and carcinogenic chemical leaching into the waterways, which is less desirable. So with the help of Emissions Reduction Alberta, we are actually developing the first commercial scale devulcanization plant in Red Deer, Alberta. So what do? We effectively have a tire-to-tire solution from the waste tires from the mining industry. We have partnered up with Liberty Tire, which is one of the largest tire shredders in North America, to work with us on this solution, whereby they're picking up the end-of-life tires at the mine sites. They will do the logistics and the pre-processing of these tires. So they basically break down these 4-ton tires into bite-sized chunks. They will then shred them down to a certain particle size that will be the input material for our clean conversions of tires into a devulcanized natural rubber reclaimed product. The way we do that is through a pure thermomechanical process without any additives or chemicals added. While we do that, the product is basically sold back into the tire manufacturing industry as a substitute for virgin rubber. So when compounding, a certain ratio will be mixed in as a replacement for virgin material. So what do? And I will preface that I'm not a chemist, so I'm not necessarily the best person to speak to the chemical aspects of the process. But during tire manufacturing, vulcanization of the natural rubber takes place, which by the application of carbon black, sulfur, basically crosslinks are being formed between the natural rubber polymers to generate strength, rigidness, and durability of this rubber in tire applications. When a tire reaches end of life, it's still vulcanized after crumbing of these tires. And in order to reuse this crumb into a new tire application, it needs to be transformed in the devulcanized state. And circular rubber, we use a planetary roller extruder that with the combination of heat, pressure, and shear forces basically breaks the sulfur bonds with very minimal damage to the rubber polymers. We've done that initially on a small scale test setup. In Germany, we have been working with University of British Columbia with the materials department to perfect our process. Then we did full modeling, whereby we basically went to commercial scale output, and we're now in the process of erecting the first facility. So why is this important? I think there's 3 main pillars. Effectively, it eliminates the landfill or incineration or downgrading of this highly valuable material. I don't know if many people know, natural rubber is a scarce natural resource. It's very carbon intensive to grow natural rubber due to fertilizer use, scarce water use during the process, the drying of the latex, and then subsequently the transportation to the tire manufacturer. So our process is roughly 85% less carbon intensive than growing virgin natural rubber, incorporating it into tire manufacturing industry. And the overall process is obviously a great enabler for circular economy and the tire industry as a whole. Up to date, Most tire manufacturers are already using recycled steel. They're using recovered carbon black. But in order to comply with the mandates that are set forward for the next generations, we need to start using reclaimed rubber in the manufacturing process of tires. So why do our customers care? The virgin natural rubber industry is a very volatile market to begin with. And as we have seen over the course of COVID, there's associated risks. Virgin rubber is primarily grown in Southeast Asia. Shipping containers were an issue. Shipping of rubber became an important cost in the overall supply chain cost of this material. Rubber trees are prone to diseases. So one year the yield of a crop can be really good. Other years it's less good. And the high overall material cost and the carbon intensity that needs to be addressed. If you compare it to our recovered or reclaimed material, which is fully sustainable and a suitable alternative to virgin rubber, like I said, 85% less carbon intensive than virgin material, 15% cost savings compared to virgin material. And it basically gives tire manufacturers stable cost levels and a localized supply on the continent where they produce their material. Our material is 100% recycled, high quality in that nature. Why circular rubber compared to some of the alternatives out there? Our clean, continuous process with a high quality feedstock being the mining tires, without any addition of chemicals or additives, gives us a very high output. Like that in combination with our technology gives the highest quality reclaim if you measure it in tensile strength. And the next leading competitor will roughly produce tensile strengths around 6 to 8, while our material yields 10 to 11 megapascal. And a very high polymer content, which is driven to by the feedstock used. Overall CO2 emissions reduction, cost reduction, and we intend to have a global supply to on each of the major continents where tires are manufactured, obviously originated by the mining sector. And as for the mining industry, it's the removal of a liability and the removal of a end-of-life tire waste problem. So we teamed up with Emissions Reduction Alberta under project name Project Roll. Our project officially started on December 9, 2022, and our expected completion date for this first scale demonstration plant is March of next year. Our project location is in Red Deer, Alberta. Overall project value is roughly 16 million Canadian dollars, and the ERA funding amount 3.2 million. Progress to date, the building is there. We have taken possession of the building. We have upgraded the lighting to the latest LED standards. We have upgraded the electricity that's needed to drive the machinery. Concrete pads for electrical equipment has been poured, and we are actually in the midst of installing our frequency converters as well as switchgear and electrical gear. And the main equipment is about to be shipped from Europe to Red Deer in the next few weeks. So like I said, the vision for circular rubber is to have global operations by the end of the decade. Our first facilities in Western Canada, and then exact rollout plan is to be determined, but we can foresee growth in Canada with an additional plant or line, and then expanding into the US and Chile as the next logical markets from a mining perspective before we enter into jurisdictions like Australia, South Africa, and the European Union. So the ERA partnership. So ERA provides us scalability and commercial potential for circular rubber's business model and technology. Our success in Alberta will basically be the jumping board to expand globally, reducing emissions and increasing revenue overall for us. And our first successful plant enables circular rubber to take the tire waste from the mining companies and deliver high quality products to North American customers overall. So I'll expand a little bit on the process, how we went about with emissions reduction Alberta. Like Mayor originally expressed, we participated in the Circular Economy Challenge in May 2022, where we expressed an expression of interest, which was successfully awarded with to proceed with a full project proposal, which we completed in September 2022, which led to a series of due diligence steps, with an ultimate funding decision being granted in December of 2022. So that was the official project start date for this project. Our first milestone was set for June 2023, which primarily involved the full design of the equipment or design of the facility, as well as the equipment procurement, which we successfully completed. I would say on schedule. July 15, we completed that milestone. We actually have been, well, we have completed that full milestone and have received funds from Emissions Reduction Alberta. So today we're still in the midst of facility retrofit and commissioning of the plant. Lab space is being done. Like I said, the facility is up, well, nearing completion as the facility itself, and then the equipment can arrive and start to get installed. Upon commissioning of the plant, which is slated for December, late December of this year, we will have a 3-month period in which we will demonstrate or gear up towards steady state operation, and then the official project will close from an Emissions Reduction Alberta perspective. But obviously, since this is a full commercial scale plant, we will carry on after that steady state operation, which is in essence a single shift operation. Then we will carry on to expand to ultimately a 24/7 operation. Our plan, well, our building is a 22,500 square foot building, capacity of roughly 15,000 ton of end-of-life mining tire can be processed on a single line every single year once we're in full 24/7 mode. This could not have been done without a great team. A few of the people here, Maartje van der Zande as our CEO and co-founder of this venture, Mark Bale-Snyder, our Chief Commercial Officer with 25 years of experience in the tire manufacturing industry, as well as the industry of selling reclaim, Paul Tournier, seasoned entrepreneur, as well as history as a consultant, where he was a partner at Accenture, helping us with strategic issues. Shauna and Raham are the boots on the ground in Red Deer, Alberta, pulling off the project, and we're currently hiring for the facility manager as well as additional staff to start completing the first plant. Jesse and Christy are primarily on the sustainability side, working on our B Corp journey. Shahid Ovi working on the Q&A and the environmental aspects of our process. Remius is our technical advisor and detailed chemical expert, and he is a special advisor advising us on normal running of the business. And that is Circular Rubber in a nutshell. I'd like to thank you for your participation today in this webinar. If there's any questions, I'll happily answer those in the Q&A session, or if there's any outstanding question, you can always reach us at info@circularrubber.com. With that said, I will stop my presentation and hand the floor back to Mer to do the Q&A session and the moderation.
Okay, thank you all our speakers. And now we have around 15-14 minutes, trying to get as many questions that we can. First, I'm going to start with a condensed response to some of the questions that came in, asking about different projects, if they're fit for our program, or what type of funding are available from Alberta Innovates, and some of the studies, if they are going to be published on our website or not. I can refer you to our website first, to our program guide. If you have any projects and you're looking for funding and information to see if your project or the scale, like the technology readiness level, is ready for our funding, you can always find information there. If you have some questions, I'm happy to respond. Just send me an email or give me a call. We can talk about that. And some of the studies that we talked about, we normally publish like a quick summary and also a final report from different projects that we support. We have a backlog right now, but we are hoping maybe check our e-library in a month or so. We are going to post, and it really depends. It has to be a public version, so it depends on the study. Sometimes it's just an executive summary, sometimes it's more, depending on the nature of project, the study, and the agreements that we have with our partners. And the question that came in about the type of impacts of some of the projects that we support, again, we have some KPIs to measure those kind of impacts. They're all in the project summaries and the final reports. You can find out more. But high level, there have to be environmental, economic, and social. On the environmental impacts, there was a question if we are looking at the full life cycle, and the answer is yes. For any project that we are evaluating, that's the big piece. We want to make sure on the LCA basis, basically there are reductions on GHG, and also we are seeing other type of environmental impacts, because with circular economy, we know it's not just about GHG. And also on other aspects like job creation, training for students, or even social aspects like supporting small communities, First Nation, all of that. These are different KPIs that we measure for any projects that we support, and we report back to the ministry to show how our funding has been used. Now I'm going to move to our first question for Karen. There is a question about pyrolysis, and the fact that you said that you did not include pyrolysis, and if you can maybe talk about why and some of the environmental impacts of this technology.
Yeah, what we didn't include it because when we first set out talking to Alberta Innovates about this, the focus was initially really on recycling, chemical recycling, mechanical and chemical. The pyrolysis, the waste to energy, is fairly well established technology, And I know, talking to you, Mayor, and Alberta Innovates, we're really looking for innovation, innovative technologies. And so we thought that was be more with the chemical recycling and perhaps a little bit with the mechanical. So just to kind of keep the scope fairly tight, that's why that was excluded. The second part was about environmental impacts.
If you have any comments on the environmental impacts of pyrolysis technologies.
Oh yeah, I'm not sure if I too qualified to answer that. Since I can imagine the greenhouse gas emissions but I don't feel too comfortable because I'm not the expert in that area. So
yeah, for sure. That question came in for all the presenters, and it's really depends on how you're going to use what's coming out of the pyrolysis technology. If it's just basically as fuel, it's there might be some concerns with that, and it's not something innovative that we would support as a project. Just a general comment. And the other question is for you, Paolo. For your final project that you described, are you looking at introducing PCR content into materials that are primarily being made from virgin feedstock, or are you looking at final products that are exclusively PCR, or both?
I needed to unmute myself. The original vision for the project was to reduce the amount of virgin plastic. So PCR as a way of bringing that down. In conversations with the industry partner, the mandate now is broader than that. So depending also on, I alluded to it, depending on the feedback that we're going to get on the market driver side, that there is also there will likely be an interest in a pure PCR product. There could be an interest also in a pure PCR product. But right now we're looking at a PCR blend up to a percentage, not full PCR.
Thank you. Bram, the next question for you. Can you speak to some of the users, like tire manufacturers, that agree to use your materials?
Sure. Thanks for the question. Currently, we have three confirmed users, all in different type of applications. One is a user that produces solid state tires for primarily forklift type applications. There is a retreader that uses to retread truck tires, and there's a user that uses it in the production of passenger tires.
So, Karen, is there a major limiting factor for bio-based circularity in Alberta and elsewhere? Access to larger scale infrastructure like large volume bioreactors.
Again, I would think the major limitation is then the feedstock source, or the volumes of feedstock. That could be sort of a limitation to the rollout of using bio-based technologies. Sorry, and I've kind of lost track of the second part of your question.
Like access to large scale infrastructure, like high volume bioreactors.
Yeah, that is, of course, that is a limitation, because there's, other than, I guess, the Enerchem type of bioreactor, I'm not sure of any other large facilities like that can utilize or transform some of the bio waste. In terms of sort of going back to this plastic circularity and using bio-based processes, that is sort of a limitation for sure, is the facilities to use larger bioreactors. But there is a possibility to kind of bring this down to sort of more local levels, sort of more scaled down. Again, there's always that issue about feedstock availability. But you can run these bioreactors or to convert biological recycling processes, you can do at smaller scales and kind of for smaller municipalities. That's, so I don't think this like it is, then it all comes back down to economics as well. So there's a lot of different things that are can factor into this. So
thank you. Paolo, when you're adding plastics waste into asphalt, do you add it, like, do you keep the whole chemical composition the same and you're just adding this component, or you're replacing any of the components by plastics waste?
Yeah, great question. So the process works like this. A company called Green Mantra sources post-consumer, among other types of plastics, post-consumer polypropylene. This is what has been used in our project. And then they have a proprietary technology to reduce the molecular weight. Effectively, it's a depolymerization process. I believe that it uses catalysts, thermocatalytic conversion for the geeks in the room. That's what it does. And the product of that conversion is in the wax range. So the waxes are then added as part of the formulation that is used to create asphalt. So it displaces some of the other components that go into creating a binder. It's a way of displacing some of the fossil fuel derived component that typically goes into a binder. So it reduces the need for extraction of virgin resources.
I see there is a question about LCA basis GHG emission, and yes, this is always a conversation about intensity, like, because we keep hearing that some of these recycling technologies are GHG intensive and maybe other type of environmental impacts. For us, it's really about LCA. I want to emphasize that. And you really need to judge it or assess each project on its own basis, because there are so many different inputs and outputs, different factors that are playing into one project or recycling of some, like, certain type of polymers, that at some point, maybe, yes, like I see this question is from Jinwen Chen. Yes, at some point it might not actually reducing any GHG or might not even have any positive environmental impacts. For us, for the projects that we would consider, we really want to look at the full life cycle and then make an assessment. And there are sometimes smaller factors that are not very big and then maybe can be negligible, but in general, we are looking at the key factors, make sure they are considered in the assessment. Bram, this question is for you. For the rubber recycling project, will the process repurpose 100% of the waste rubber, or is there a waste stream at the other end of a portion of the rubber you process?
Thanks for the question. No, on a pure mass balance, it's 99.9% what goes in does come out. So obviously the steel that gets removed during the shredding process gets recycled. The fibers that they remove get recycled as well. And then we take a pure rubber crumb stream from Liberty Tire, and that rubber crumb stream, it goes out, what goes in comes out for 99.9%. There's a little bit of thing coming off, which gets filtered, but on a mass balance perspective, 99% comes out.
So this question, I believe, maybe Karen, you would be the right person to respond. It's my understanding that the Canadian government has eliminated PHAs as a traditional plastic replacement option, with its new rules banning various single-use plastic products. Is this a shared perspective? And if so, what are the groups hosting this presentation doing to advocate for these promising materials? I have to imagine that they constitute at least part of the solution to the challenges we are facing. Maybe before I pass it to you, I can say that we normally, Alberta Innovates is supporting technology side. We are not advocating and we are not part of any policy making decisions. But yeah, I will pass it to you, Ken.
Yeah, I mean, I was not aware of that actually, that governments was not advocating or phasing out the PHAs. That's interesting. Yeah, I can't say any more to that. So.
Okay. Anyone else has any ideas about that? And I think now we are getting close to the end of webinar. Thank you for all the questions. Sorry we couldn't get through all of them. Thank you so much to all the speakers and for sharing about their projects today with us. And thank you all for joining the webinar and listening to us. If there are any follow-up questions, any contacts, we are always happy to hear from you. Okay, thank you and goodbye all.